Alright, so welcome back to particle physics and a standard model. This is lecture 13. Okay, so last time we brushed up the concepts of angular momentum and total angular momentum and its associated quantity, the spin angular momentum that you see only in quantum mechanics, and then we saw how to add angular momenta and hence how to add spins and determine that mesons have integer spins and baryons containing 3 quarks should have half integer spins, right. And we also worked out what values should be taken by the total angular momentum of mesons, and in particular we saw that that should also take integer values, correct. So let us end our discussion on angular momentum with what is known as Clebsch-Gordon decomposition. So no discussion of angular momentum in quantum mechanics is complete without this, right. So what is that? Clebsch-Gordon decomposition, which is a very useful tool to determine probabilities of certain states. Okay, let us see what it is. So let me write the equation first and then explain what it is. If I had a state described with 2 particles, one with total angular momentum J1 and then the Z component M1, the other with J2 and M2. Okay, these need not be just 2 particles, these could be just 2 different states themselves. Okay, but I am combining them together to form one single state. Alright. There may arise situations where I want to know the probability that I can measure the total angular momentum as J in particular, some J. Okay, this is the reverse of what we had seen before, right. So J, if the total angular momentum was J, then you know the total angular the eigenvalues could have ranged from J1 minus J2, the absolute value, all the way to J1 plus J2, right. This is sort of the reverse problem. If I had a state, if I had already measured a state in J1 M1 and J2 M2, I want to know what is the probability that the total angular momentum is some capital J. Okay, so if I put it that way, what should the values of J range from, capital J? I just said it, right. It should go from the magnitude of J1 minus J2 all the way to magnitude of J1 plus J2, correct. Okay, so obviously what I am writing here is a quantum superposition, right, which means I have the requisite coefficients in front. So for this particular J, I have the coefficient, for the coefficient I am going to label it with J, and since I started with a J1 J2, that coefficient corresponds to that, and the total M angular momentum is obviously M, M1, M2. Okay. Now at the end of the day, this is the state that you are going to measure, right. The wave function is going to collapse into one of these states, correct. So that is the measurable, and these are the coefficients right, which you can derive from everything that we learnt about angular momentum in quantum mechanics before, right. We are not going to do this in this course, you can look up how to do this derivation, but it is not so easy, sorry, it is not so hard, right. It is not trivial, but it is not hard either, alright. So since these are derivable, you can look them up in tables that are provided all over the place on the internet, in textbooks and so on. Griffiths has one such table. Okay. So this coefficient or these tables are called Clebsch-Gordon. coefficients. Alright, so these tables are called Clebsch-Gordon tables, and this whole procedure is called Clebsch-Gordon decomposition. Okay, so alright, this might sound a bit abstract, but let us look at a real life example. This is given in, for example, Griffith's worked out example, I believe it is 4.3, go look this up in chapter 4. So it goes like this, right. You can always prepare an electron in a hydrogen atom, right, with some angular orbital momentum L and the corresponding orbital momentum z component of the orbital momentum, orbital angular momentum Lz. Okay. So that corresponds to the J1M1 here now. Okay, do not be thrown off by the notation here. Okay, this is a generic notation, but it could apply to any kind of angular momentum, right. So now I am writing the orbital angular momentum, but of course the electron also has a spin. So I can also specify what the spin is, correct. How do we usually write this? We write it like this also, right. So I am just going to write both the notations. So this basically describes all the angular momentum quantum numbers of an electron in a hydrogen atom, once I specify what L and Lz and all that are, right. Now given this, I might ask, what is the probability of finding the electron in a state given by basically capital J, right, that is J comma basically Jz, let us just say that. The Z components add, right, Lz plus Sz is basically Jz, right. In other words, if I apply the J square operator, then I should get J times J plus 1 as the eigen value, right. So what is the probability of measuring a J square of a certain eigen value? So this is the kind of real life question that can be answered using Clebsch-Gordon decomposition. Okay, so there might be 1 or 2 assignment problems on this. All right, beyond that we will not be worrying about it too much for this course. Okay, so that done, we are done with the eigenstate, eigenvalue aspects of angular momentum. Let us go on to other fun aspects of spin itself. Okay. So let me open a new page for that. We are going to get used to the notion of spinors. Okay, and I am going to write this because this is important. Spinors in quantum mechanics. Okay, this is not spinors in quantum field theory. Okay, these two have the same name, but they have kind of little to do with each other. Okay, do not get confused. So later on we will encounter spinors in quantum field theory. In my opinion, this is what should be called spinors, the quantum field theory one. The one in quantum mechanics, in my opinion, should be called spinors, because this is literally something that you put into a spin rotations in real space, that which carries the quantum mechanical spin, whereas spinors in quantum field theory are a completely different beast. We will see what they are when we learn about Lorentz group representations and all that. Okay. So what are spinors in quantum mechanics then? What does this word imply? These are basically representations of spin half states. Spin half states are fermions, right? All fermions are not spin half states, they can be any half integer state, but all spin half states are fermions, correct? Okay. So, that would automatically mean that the z component has eigenvalues plus or minus half, correct. But I do not have to always specify the z component this way. So, one trick I can do, which we have already used implicitly, is to represent these states in the Ket notation with an up arrow and a down arrow, spin up, spin down, correct. Okay. Further, I do not have to stick to the Ket notation, right. So, this is S comma Sz, right, that is the notation I am writing it in here, but the Ket notation I can use matrix notation obviously, right. Often matrix notation turns out to be a lot more useful. So, the spin minus half state I am going to represent with a 0 comma 1 0 1 with a 2 row column, single column, and the spin half state, the up state I am representing with 1 comma 0, right. Okay. Now, should these states, should a spinor, a spin half state always exist only in one of these two? No, not necessarily. Remember that we arbitrarily chose the z component to be the state, to be the operator that we measure simultaneously with the total spin angular momentum, right. So, it could have been in any direction, basically the spins could be pointing in any direction, right. So, generically I can write a spinor as some coefficient of the up, but in the z direction, and then down in the z direction, right, as long as obviously alpha squared plus beta squared, of course these can be complex numbers. So, I am taking the absolute value as long as they add up to 1, right, very good. Okay. That is some good brush up. So, if I can represent the spin states with 1 0 0 1 and other combinations, right, as long as I can represent the spin states with a 2 cross 1 matrix, a column matrix, then I should be able to represent the spin operator also as a matrix, right, stands to reason, correct. So, who remembers what these operators look like? These are some famous matrices, correct. So, what is this? The spin in the x direction, that is of course H cross over 2, the Pauli matrix, right. So, let me write that out for you, the first Pauli matrix. Correct. And similarly Sy is the second Pauli matrix. So, I think I am getting the signs correct, but it is up to you to really check it, alright. And of course, this should be easy to guess, because this is the direction that we chose for our reference, it is just 1 minus 1, right. Now, who remembers the commutation relations and the anti-commutation relations of Pauli matrices? If you do not, I very highly recommend deriving for yourself, okay, the commutation relations and the anti-commutation relations. You have to do this once on your own, it is very easy, I have just written down all the matrices for you, right. So, go ahead and do this and you will never forget it, okay. This is one of the most important things you should remember in quantum mechanics, in physics, in the all of physics, okay. But I am going to write down the answer now in a shorthand notation. Both the commutation and the anti-commutation relations can be simply written this way, with the indices, the I and j obviously run over x, y and z, right. So, sigma I sigma j is delta ij, which is the Kronecker delta, plus I, this is a complex I, okay, do not get confused with the index, the Levi-Civita tensor epsilon ijk, completely antisymmetric tensor, remember, times sigma k. So, you can check for yourself, right, if I is equal to j, then it does not vanish, right, that is exactly when it does not vanish, the anti-commutator does not vanish. So, I just get a delta ij, but then when I equal to j, the second term vanishes, correct. When I is not equal to j, you keep the second term in the commutator, correct, but then check for yourself what happens in the anti-commutator, right. You can manipulate all the indices and check, cross check against what you got. Okay, that is excellent. So, we can go on to the other aspects. All right. So, now that we have written the operators this way, it is not hard to guess what the eigenvalues are. The eigenvalues are always going to be plus half and minus half, correct. But what could the eigenstates look like? This also I highly recommend for you to go and derive yourself. You know how to do, how to write the characteristic equation and get the eigenstates and the eigenvalues, right, the eigensystem. So, I am going to write down for one of these cases, for Sx, how the eigenvalues look like, sorry, eigenstates look like, or said differently, the eigenvectors would look, this is the usual notation, or at least the notation used in Griffiths. One of the eigenvectors would be basically 1 and 1 suitably normalized. So, I have a square root of 2 in the denominator, the other one would be 1 minus 1 suitably normalized. Okay. So, similarly you can go work out what the eigenvectors are for Sy. For Sz it is trivial, right, 1 0 0 1, we already wrote that down, alright. Okay. Excellent. Now, what are the eigenvalues of Sx squared? So, let us go back, right. Sx was sigma x up to a proportionality constant, right, and we just saw what the commutation relations were and the anti-commutation relations, and we just saw that sigma x squared, right, should basically be identity, right. You can see it from the matrix here, you can also see it from the commutation relation that I have written down here, right. So, sigma x squared is nothing but the proportionality constant squared, which is h bar squared over 4 times the identity, right. Okay, that is trivial to see, but what does it mean physically? Physically it means if this acts on some spinor, okay, alpha beta, any spinor oriented in any direction, you are certain to measure h square over 4, h bar square over 4. What do I mean by that? The probability of measuring that is 1 basically, that is what an identity exactly means as far as operators are concerned, correct. So, any spinor oriented in any direction, you hit it with Sx squared, you will measure its eigenvalue with probability 1, okay. So, similarly for xy squared and sz squared, right. So, now I can write the total angular momentum sorry, spin angular momentum, the square of course, as this. What would this give me as the eigen value? Again, if I hit it on any spinor oriented in any direction, I am certain to get the eigen value as 3 h bar squared over 4, right. Well, in a sense we knew this already, right. I did not have to do this in this way. Why is that? Because we knew that the eigen value of the s square operator was small s square, sorry, for the s square operator the eigen value was s times s plus 1, right, small s times s small s plus 1, of course with an h bar square, correct. And obviously if I now plug in s is equal to half, I am getting 3/4 h bar square. So, we knew this already, we are just cross checking all this by actually explicitly writing down one representation of matrix operators. Okay, excellent. Then what is the use of writing all these spinors? Well, it gives you one way to represent the spinors with matrices, but what is the real use of all this? Okay. Why do we call them spinors? I told you in quantum mechanics I would like to call them spinors, right. What do I mean by all that? Well, you can obviously take a spinor again oriented in some direction and rotate it, okay, with some operator. For now I will put a question mark here, rotate it and get another spinor. And when I say rotate, I do not mean rotate in some Hilbert space or rotate in some abstract space. No, I mean real rotation, rotation in real space, in the real 3D space that you are sitting in. Okay. How can this be done? So, obviously we can think of a suitable rotation operator. I am going to call it U, and since I am talking about rotation, I can think of a rotation angle, correct. Not only that, I have to orient the rotation, right, in a certain direction, correct. I have to do the rotation around a certain direction, correct. That means it is not just theta, it is a theta vector, okay. So, let me once again clarify, what does this theta vector mean? It means I am doing the rotation along some direction, okay, which points along some theta vector, some theta cap, right, in xyz plane, right, with magnitude theta. So, that is what this shorthand notation means, okay. Now, what is this u of theta? So, go look at Griffiths for how this comes about, okay. This u of theta, this operator turns out to be, so here you go, exponential of the following matrix, theta dot sigma vector over 2, okay. It should be easy to guess what the sigma vector is, right. It is nothing but, I am just writing the Pauli matrices on some 3-dimensional plane basically. The 3 Pauli matrices you can represent in some space, okay, as a vector, right. That is what I have done, the 3 components, the three matrices, right. Okay. So, If you are not familiar with exponentiating a matrix, now is the time to get familiar with it. Okay. Let me just briefly write the formula for the expansion for an exponential of a matrix. What is that? What is the first term? Obviously is identity plus a plus a square, the 2 factorial and so on. This might look trivial, this looks just like as though a is an ordinary number. No, it is not. Here a is a matrix, and so all the rules of matrix algebra apply here, right, especially when you take determinant and trace and things like that, correct. Okay. Now further, once I have given you this, once again I am going to leave this as an exercise to you. Go expand that exponential, okay. Where is that exponential? So, expand e power I theta dot sigma and get u of theta vector equals cos theta over 2 times the identity minus I, in this case it is literally the direction of theta dot sigma sin theta over 2. Okay. This is how you rotate the spinors. Okay. To make this look easier, I am just going to expand this into the 2 by 2 matrix, that literally I am just going to write this as a 2 by 2 matrix, right. So, that is nothing but cos theta over 2 minus I, what is this now? This is theta z, right. That is the only polymatrix that has a diagonal element, correct. So, I have this, and then down here the expansion gives me I sin theta over 2. There is a nice pattern to this, as you can see, right. Once you write it down, it looks a bit intuitive, correct. So, minus I sin theta over 2 theta x minus, right, because I know this has to be unitary, correct. Polymatrices are unitary, so expansions in terms of those should also be unitary. Cos theta over 2 plus now okay. Very good. That now is the operator that you would use to rotate spinors in real space. Okay. Get used to looking at this operator a bit, alright. So, let us look at 1 or 2 examples of what this operator will do for you. Okay. Suppose my theta was actually a 2 pi rotation around the y axis. Okay. I am taking my spinor wherever it is pointing and then I am going to rotate it around the y axis, right. You can use your wrist to rotate it, right. Okay. What is going on then? What would you get as u? Do this by yourself and you will find that what is going on here. So, cos of, I have cos of pi, correct, and that is a minus 1, and then everywhere else I have sin pi, that is a 0, right. So, here it is 0, here it is 0, here it is 0, here also it is 0. So, I am left with another cos pi, that is also a minus 1. correct. Does this look familiar? This is just what we are talking about when we discuss the spin statistics theorem, correct, that when you rotate a spinner by 2 pi, it does not come back to itself, it comes back to -1 of itself, right. This basically flips the sign of the spinner, and then you rotate it by 1 more 2 pi, it will go back to what its original is, correct. And this is a very unique thing about spinors, it is a very quantum mechanical thing, and in quantum mechanics it is possible, right. Why is that? Because in quantum mechanics the real observable is the square of the mod of the wave function, which is what gives you probability densities and so on. That is really what is observable, right. So it should not really matter if the wave function, in this case represented by the spinner, right, that state picks up a minus sign, right. It is okay if it picks up a minus sign. So that is what is going on, and since spin is a purely quantum mechanical concept, it is totally allowed and it does make use of its freedom in nature, okay. So let us look at one more example and then I will close this lecture. So let us take theta to be just pi. Again, without loss of generality, I am going to make this point in the y direction. So what happens then? If I rotate by pi, what do you expect? You generally expect, we usually say at 180-degree turn, right, that is what it is. Does this happen for spinors also? We can check that. Once again you see that, see what happens to cos theta here, see what happens to sin theta, okay, here, here, here and so on, alright. So I am not going to do it right now, this is for you to check, I already did one matrix for you, right. But the net result is that if I apply it, if applied to 1 0, that is the simplest case, right, a spinner pointing in the z direction upward, it should give me basically 0 1. So I flipped the spin, and vice versa, if I apply to 0 1, it should give me 1 0, okay. It should be very easy to check, alright. Okay, so I will end here and then in the next lecture we will see more general cases of unitary matrices such as the ones that we have been dealing with, and then we will see how the space of spinors lives in what is known as an SU2 group, and that the set of all these rotation matrices constitutes the SU2 group, and that is our gateway to continuous symmetries, group theory and so on. This is something that we have already seen in non-relativistic quantum mechanics, but we will see more and more versions of this when we move on to quantum field theory, okay. Alright, thank you then, see you in the next class.